For decades, physicists have dreamed of harnessing the power of the sun, building a star on Earth. This is the promise of nuclear fusion, not science fiction, but a real scientific quest. Unlike nuclear fission, which splits atoms, fusion fuses light atoms like hydrogen, releasing immense energy, the same process that powers our sun. Imagine a world with limitless clean energy, no carbon emissions, no long-lived radioactive waste. Fusion could solve the energy crisis and climate change in one stroke. But achieving fusion is profoundly difficult. We need temperatures over 150 million degrees Celsius, 10 times hotter than the sun's core. At this heat, matter becomes plasma, a superheated soup of charged particles. No material can contain plasma, so we use powerful magnetic fields to trap it, creating a magnetic bottle. This is the core challenge of fusion energy. Since the 1950s, scientists have built experimental devices, each pushing the boundaries of knowledge. We've learned to create and sustain plasma, heat it to unimaginable temperatures, and build the magnets to contain it. Progress has been slow but steady. Each step brings us closer to a miniature sun on Earth, a clean energy source for all humanity. Achieving fusion would fundamentally shift our civilization's relationship with energy. Our world runs on fossil fuels, oil, coal, and gas, which have powered us for centuries but at great environmental cost. Fusion offers a way out. Its fuel, hydrogen isotopes, deuterium and tritium, can be sourced from water and lithium, making the supply virtually inexhaustible. Fusion energy could mean a future where energy is abundant, clean, and a source of prosperity, not conflict. The journey is long, but the prize is worth it. Fusion is not just a scientific challenge, it's a vision for a better world. The dream of a star in a bottle continues to inspire scientists and engineers worldwide. The next step in this journey is the construction of the world's most ambitious fusion experiment. This is where the story of ITER begins. The quest for fusion is humanity's boldest energy gamble. In southern France, a monumental project called ITER, International Thermonuclear Experimental Reactor, took shape. 35 nations joined forces, pooling resources and expertise to build the world's largest fusion reactor. ITER's mission proved that fusion energy can be produced on a large scale. Its goal is to generate 500 megawatts of fusion power from just 50 megawatts of input, a tenfold energy gain. Achieving this would be fusion's Kitty Hawk moment. The scale is staggering. The reactor building towers over the landscape. The tokamak weighs 23,000 tons, 3 times the Eiffel Tower. Thousands of engineers and scientists from around the world designed and built its complex components. Each piece pushed the limits of engineering and materials science. ETR is a cathedral of science, a testament to global collaboration. The cost is enormous, running into tens of billions of euros. Critics question if the money should go to renewables like solar and wind. But ITR is a high-risk, high-reward bet, a necessary gamble for a technology that could transform our world. The project's success or failure will shape the future of energy. ITER is not just a machine, it's a symbol of what humanity can achieve together. The world is watching to see if this gamble will pay off. The stakes could not be higher. The next chapter, building a tokamak like no other. At ITER's heart is the tokamak, a giant, donut-shaped vacuum chamber where fusion happens. The ITER tokamak is the largest and most advanced ever built. Inside, a few grams of hydrogen fuel are heated into swirling plasma, recreating the conditions of a star. To contain this plasma, ITR uses superconducting magnets cooled to near absolute zero, colder than deep space. These magnets generate fields hundreds of thousands of times stronger than Earth's, creating an invisible cage for the plasma. The magnet system is a marvel. 18 massive toroidal coils, a central solenoid, and 6 poloidal coils, all working in harmony. Each component was built by different nations, then shipped to France and assembled with millimeter precision. The engineering and logistics were unprecedented. The assembly of the tokamak was a global effort, requiring extraordinary technical skill. Every part had to be perfect. Even the smallest flaw could threaten the entire project. The tokamak is a triumph of international cooperation. It represents the cutting edge of science and engineering. But with such complexity comes risk. The world waited for ITER's first plasma, a moment decades in the making. Then a cascade of anomalies changed everything. 2025 was to be ITER's landmark year, its first integrated tests. The goal, create a stable plasma and ensure all systems work together. But as commissioning began, trouble emerged. Sensors detected unexpected temperature fluctuations in one toroidal field coil, TF coil 7. At first these seemed like minor glitches, but the anomalies persisted. Micro vibrations and further data pointed to a real issue inside the coil. The team paused the schedule and launched an investigation. Then, during a low-power test, a sudden energy discharge, known as a quench, occurred in TF coil 7. Safety systems shut down the reactor instantly. The quench was proof of a catastrophic flaw. ITER, the world's largest fusion reactor, was shut down indefinitely. The investigation was painstaking. Using robotics and advanced imaging, engineers mapped TF coil 7's internal structure. The culprit, a microscopic fracture in a niobium tin strand, likely from manufacturing years earlier. This tiny flaw grew under immense electromagnetic forces, creating resistance and heat. During testing, it triggered the quench that shut down the system. The flaw was not in the design, but in manufacturing and quality control. Now, all 18 coils were under suspicion. Repairing or replacing them would be astronomically expensive and time-consuming. News of the shutdown sent shockwaves through the physics community. Some saw it as a painful but valuable lesson in quality control and the limits of mega-projects. Critics argued that putting all resources into one giant experiment made the field vulnerable to single-point failures. Others called for a more diversified approach, funding multiple, smaller fusion projects. Project leaders urged patience, emphasizing that scientific progress is built on learning from failure. The safety systems worked, no one was harmed. The problem was identified, and the international team would work to fix it. The incident sparked debate about the risks and rewards of big science. ITER's failure is a humbling reminder of the challenges in building machines of unprecedented complexity. It will be studied for years as a lesson in engineering and international collaboration. The dream of fusion is not over, but the path forward is more uncertain. The world must decide how to balance ambition with resilience. The next steps will shape the future of fusion research. ITER's failure triggered political and financial shockwaves among its 35 partner nations. The flawed coil, built by European and Japanese industries, raised questions about liability and cost sharing. Repair costs could reach billions, straining the project's finances and unity. Tensions grew over quality control standards and the in-kind contribution model. Thousands of scientists and engineers faced uncertainty about their futures. Graduate students and researchers saw their projects put on hold. The risk of a brain drain from fusion research became real. The spirit of global collaboration was under its greatest test yet. Despite the crisis, a recovery plan is emerging. All 18 coils will undergo rigorous new testing using advanced inspection technologies. Rebuilding trust requires transparency and improved oversight. Replacing a coil means disassembling much of the tokamak, a slow, costly process, likely taking at least 5 years. Quality assurance protocols across the global supply chain will be overhauled. The lessons learned will strengthen future fusion projects worldwide. Diplomacy is as crucial as engineering. Renewed political and financial commitment is essential. ITER's future now depends on both technical solutions and international resolve. ITER's shutdown is a blow, but not the end for fusion energy. It may energize the private fusion sector, where startups pursue diverse, innovative approaches. Governments and investors may now support a broader portfolio of fusion concepts. The lessons from ITER's failure will benefit the entire field, improving safety and reliability. Even in failure, ITER fulfills its experimental role, providing critical data for the future. Science advances through both success and failure. The quest for fusion is a marathon, not a sprint. The dream of a star in a bottle remains alive. The path is longer and more complex, but the resolve endures. The work continues in ITR's halls and in labs around the world.